slides, you can see that there's a typo in the first slide. It's not. We went back to lunch and came back a year later, so apologize for that. All right, so I'll talk about multi-stage stochastic optimization. As you've seen in this morning, stochastic programming involves a lot of notation. There's going to be a lot of it in this session as well. Unfortunately, I wish I knew a way to avoid it, but there is a lot of notation. So I may not be able to finish everything that I intended to cover here, but let's try to see how far we can go. All right, and please, ask me questions in the interim. It's okay if you don't finish everything that I would like to cover today. All right, so here's the outline, the plan. So I'll talk about the problem, kind of the setup, and the issues that needs to be modeled for modeling a multi-stage stochastic programming problem. I'll talk about 3 formulations. You've seen all of these already in the 2-stage setting. I'll just try to kind of refresh your memory and see how those things extend to the multi-stage setting. Then I'll talk about some algorithms. All right, so and these algorithms essentially kind of use the different types of formulations that are presented here. All right, so here is the canonical multi-period deterministic optimization problem. So as I said, there's going to be some notation, so let's just parse through this. So we're talking about a finite horizon problem. That's very important here, that we have a finite number of stages or decision stages, finite number of periods, that's capital T. We have an objective function that is involving 2 sets of variables, xt and yt. Here, xt is going to be what we call here stage variables. Essentially, they capture all the information that is necessary to link multiple stages together. And then there are these kind of local variables or stage variables, which are kind of only variables that has to do with actions within that particular stage. I'll try to make this clear with an example in a bit, but this distinction is important for some settings, and I'll allude to that later on. In this particular talk, we're just going to concentrate on linear objectives and constraints. So this is essentially a linear function, and this is the constraints that link the different time periods. These are the constraints corresponding to each stage. And here, as you can see, we did the dependency in a way that the decisions in stage T only depend upon the state variables in decisions in T minus 1. Obviously, you could have decisions or kind of interactions across more stages, but you can always model this by introducing kind of auxiliary state variables that capture kind of the dynamics in that way. Yes?
So the capital T is a constant, right?
Capital T is a constant. Not for this talk. It's a constant. It's a deterministic thing. So this is the objective function. This is the constraint set. Again, we have a constraint set for every time period. The only linking between them is that the variables in T minus 1 appear in the constraint system for time period T. This is a sufficiently general formulation for a deterministic problem. If you you can model it. If you have other types of dynamics, you can always formulate it in this way. We're going to assume that this problem is bounded and feasible. And so here's a kind of a simple example, but actually kind of used in practice. So this is kind of a hydropower plant. We are interested in, so we have a number of planning periods, say quarters, for example, and in each quarter we are interested in how much of hydropower to generate here, right? So essentially to satisfy demand. So there's demand is known, and so what is the other issue is that how much water flows into the reservoir in every period. So that's something that could be uncertain, but here we're talking about deterministic formulation. So here's my simple model. All right, so let's again parse through this notation. So we have a bunch of time periods. This HT is the head, the amount of water in the reservoir. And so HT in time period T depends upon how much water was there. HT minus 1 in the previous time period. How much water came in through, let's say, rainfall. That is CT. PT is how much water was used to produce power. That's P of T. And then I have some kind of these artificial variables, essentially to make the problem feasible, but also kind of it's quite reasonable. UT is like water that I pump back into the reservoir. For example, if the reservoir is kind of is depleting too much, you want to pump back things, or how much water that I spill. That is water that is spilled without generating power. Right? And so there are associated costs of these things. This is this is the dynamics. This is the constraint that links different time periods together. And this is kind of the power balance constraint. So this is demand of power. So this would be, for example, in meters. This would be in kilowatts. So this is, and so PT is in meters, how much water was left out, or meter cubed. This is the coefficient of transformation. We are assuming a simple linear model, like, okay, how much water gets converted into power. This is the amount of power that I generate. QT is the amount of power that I buy from the market outside. So that's kind of spot, using spot prices. I just buy power for the market if I cannot satisfy demand using this hydro plant, right? And so this just says you have to equate it to the demand that is in that time period. The costs are cost of buying power, cost of pumping water up, or costs of kind of spilling. Maybe there's some penalty for spilling water. The head has to be within some bounds. So this would be kind of a very simple multi-period optimization problem if we knew the entire demand history or demand forecast accurately and how much water is going to come in. All right. So let's talk about what are the kind of the state variables in this model. So x of t is the water that is in the reservoir is my state variable. Right? If I told you that in every time period what is the state variable that you have, here's how much water you should maintain in the reservoir in every time period, then the problem kind of separates into every time period separately. You just have to optimize what is the minimum cost way to meet your demand to satisfy all of these constraints while maintaining this water in every time period. Right? So this is what I call by local variables. So is the distinction between the state variables and local variables clear to everyone? All right. Any questions about this formulation? Okay. All right. So let's talk about kind of the stochastic setting now. Right? So again, I've just repeated kind of the canonical deterministic problem up here. So now we have data for the problem, which is not known precisely. So in this case, let's say there are some objective functions. This is some notational abuse. There is some objective function coefficients. That's this. There are some constraint coefficient, which is capital X of t. This is uncertain. Right? So in the stochastic programming setting, as you've seen, we model these as a stochastic process. It's a multi-period process. There is some underlying stochastic process. We assume that we know kind of the distributions and everything in this setting, or we're able to sample from it. So there is an underlying stochastic process with all the kind of the underlying model known. That's again an input to this model. So the starting point is the deterministic formulation. Then the second element is to know what is the underlying stochastic model. Right? I'm not going to talk about that, but we assume that there is something like that in there. And then there is the dynamics. Right? So because it's a multi-period model. In the two-stage model, you've seen that we make a first-stage action, then we observe something, then we have a way to correct that action, like a recourse action. Right? So that's a two-stage, and then the game ends. Here, it's a multi-period setting, so there could be very different types of dynamics that goes on. Right? And so that is also an important modeling choice or important feature of the problem. So in this particular setting, we are going to assume that we have the actions from the period t-1. Then we observe the information, the realization of this random stochastic process for that time period, and then we take the action for the next period. All right? Of course, I mean, things may not be in this order necessarily, but you can model it depending upon what the actual dynamics are. So this is what I call the dynamics of how decisions and the information are kind of interacting with each other. Okay? So now here is the kind of the formulation, a formulation. It's not much you can do with this formulation, but we should put it up on the board. So let's talk about what this is. So we'd like to minimize. So in this particular formulation, we're interested in minimizing expected costs. All right? So what is the expected cost? Because now we are taking actions in every stage. So given everything we knew before, we'd like to minimize, let's say, the cost of the last period. Right? But that depends upon what all has realized before, so you'd like to minimize the expected cost of that. And so you fold back, in the previous periods, essentially what you're interested in. You'd like to minimize the sum of the first stage cost plus the expected cost of everything that happens afterwards. So what happens afterwards? You take a second stage action where you minimize the sum of the second stage cost plus the expected cost of whatever happens afterwards from stage 3 and so on. So you have this kind of nested formulation. So an important thing to note here in this formulation is that these expectations are with respect to the conditional distribution at stage t. Right? So when we have, let's look at stage 2 onwards. Right? So in stage 2, you have observed a particular realization of your stochastic process, and then whatever remains that distribution depends upon what you have observed, if there is interstage dependencies. It depends upon what you have observed. So the expectation that goes on here, that is expected cost of future, should depend on the observation that you've made in that period.
How is this different from just a two-stage setup where you have x1, y1 being optimized with respect to expected value or all possible C's?
Because a two-stage model would end here, right? So you would have...
if I include all x2 through xt as the decision variable for...
Yeah, so let me go back to, I'll address that question when we talk about the two-stage approximations of this problem. And that's a good question.
Why is it an approximation?
Let me tell you that. I'll tell you that, okay? All right, so this is a natural extension of a two-stage formulation. So here is an important thing that I think Dave alluded to this in the last lecture. So what is the solution to this problem, right? So when we talk about a two-stage model, how do you encode a solution? So you can say, okay, here's the optimal first stage decision. Because once you give me the optimal first stage decision, I can compute what the second stage decisions are, right? Given the uncertainty realization and the first stage, so essentially you can report the first stage solution. That's why in all of those problems we talk about, okay, minimize x, f of x, where this is actually the expected cost of some, you didn't use f, but some other function, which is again some expected value of some optimization problem involving x and y second stage decisions, so right? But we don't really care about the second stage decisions y's. We only care about the first stage decisions in the two-stage model. So there is a way to, the solution is, these models are in that sense very, almost like a deterministic optimization problem, because there is a finite dimensional decision vector, there is a function, and you're interested in optimizing it, right? So that's why we can use all of these convex optimization algorithms to solve this, because everything is hidden here. For this function, you can evaluate it, you can get its gradient, and then so on. Here, what is the solution? Because if I told you the first stage action only x1, you need to know what the second stage action is going to be, and that gets kind of these decisions in stage T depend upon the history all the way to in stage T. An analogous way to think of this is like, okay, if I want to know both x and y's, so you'd have to report x and y for all possible realizations. That's not easy to encode, right? Unless you have a list of scenarios, you can say, okay, here's x, here's y1, here's y2, here's y3, and that you can report it as a table. So in this case, so that becomes an issue. It's not easy to see how to encode these solutions. We are going to assume for the rest of this talk that this complete recourse assumption, where basically for any value of state variables, any value, so this is even not it's stronger than relatively complete recourse. So whatever value of the state variables you give me, there are some local variables that can adjust to make the stage-wise problems feasible, right? So for example, in that hydro example, I always had, you could pump up water or spill water. So doesn't matter what heads you want, I can always make that happen. Is that okay? Good. All right. One thing that I want to point out here, this notion of a stage, and this goes back to kind of your question, depend on the dynamics, not on the number of periods. Okay, it depends upon what the actual decision dynamics are. So consider this dynamics. So here, one thing that I can do is I can decide the values of the state variables ahead of time. So my solution is that, okay, in January, this is how much water I want in the reservoir. In February, this is how much I want. I give you those things. And then, you figure out how you should generate the power and what you should do depending upon how much inflows are there and what the demand is, right? So you decide X1, and then you observe the water inflows, and you decide Y1, and so on. But once you decide the state variables, these problems are completely separable, right? There's no time dynamics involved at all. So basically, this problem is the same as deciding the values of the state variables and then observing the entire realization of the stochastic process, not in between, but the entire process, and then kind of deciding what the y should be. this would be a two-stage model. Okay, so this is different from the dynamics that I talked about, and I'll come back to this more later on. Is that clear? So here, this is a two-stage multi-period model, not a multi-stage multi-period model. Okay, 2 is not multi for our purposes. For most purposes, it is, but not here. Is that okay? Good. All right. All right, so plenty of applications. In particular, energy. There's been a lot of kind of interest on kind of applying multi-stage stochastic programming to energy. This is kind of a book where on application of stochastic programming, which has several examples. All right, so one thing that I mentioned here is that, okay, so we have the core deterministic model. We have the dynamics, the kind of decision dynamics we'd like to model, but we need an underlying stochastic model, right? How the information is being revealed. So I'm going to talk about kind of algorithmic things. So we're going to assume that we have a finite dimensional setting. In other words, we're going to assume that our stochastic process is given to us in the form of what is known as a scenario tree. Okay, it can be huge. It can be very, very large. But essentially, it tells us that, okay, here is what happens in period 1. Everything is known, right? So what is a scenario tree? In period 1, I give you this is the data for period 1. In period 2, there are, let's say in this example, there are 2 possibilities. Right? So you have, that's why we have these different nodes. Nodes tell us realizations of the information, of the data, right? And you have probabilities associated with this node. Then period 3, conditional upon what happens, there are these 2 possibilities. Or if this happens, there are only a single possibility. So you can imagine that there is a stochastic. The stochastic process is modeled by this tree. Okay, this is known as a scenario tree. How do you construct one? I don't know how to present that because that's a very, very difficult subject. There are many, many things that one can do. There are discretization, explicit constructions. You could produce that by, for example, doing sampling, right? So you have a stochastic process, and you do conditional sampling in each stage to construct a tree. Right? So you have the deterministic data for this period. For the next period, okay, let's say I generate 10 realizations. I have 10 samples. And based on that, sample 1, now I know the distribution, the conditional distribution based on that. Based on that conditional distribution of the realization in stage 1, I generate 10 additional samples, and you can construct a tree like that. There could be the tree could be implicitly defined. Okay, so again, this will become a little bit more clear later on. Essentially, I don't have to give you kind of this tree, but there could be an underlying Markov chain, for example, which means that there is some stage-wise independence. So you could move from any node to any other node in the next stage, independently. That could be implicitly a Markov chain defines a tree of this kind. All right? So I will get to that later on. Okay, so let's talk about formulations. So I'll talk about extensive form, scenario formulation, and dynamic programming formulation. Here's the extensive form, right? So remember, what are we going to do? We're going to associate, so I talked about encoding solutions. So now we have a scenario tree. Let's talk about some notation here. So n is the index of a node in this tree. A of n is the ancestor or the parent node of the tree. All right. Pn is the probability associated with that node. So this is the kind of the. Let's say, is there an example later on? No, so I don't have an example. So the probability of this node is 1, for example. The probability of this node is going to be, let's say, half. This would be 1/4, 1/4, and so on. Right. So we associate a decision variable, xn and yn, corresponding to every node of the tree. And so we are interested in minimizing the expected total cost. So essentially, we sum up over all the nodes of the tree, take the probability times the cost associated with this node. That's the total cost of your actions in this problem, for this multi-stage problem. And the constraints basically say I have a constraint for every node of the tree where the decision variables are xn and yn, and they only depend upon the decision that was taken in the ancestor node or the parent node. Is that okay? So this is kind of a straightforward extension of this extensive form for two-stage problem that you've seen, or deterministic equivalent that you call it, right? So here is the matrix structure that you have for this particular tree, right? So in the extensive form, you would have seen something like you would have first-stage variables and a kind of a blocks of second-stage variables. Here it looks a little bit more interesting, so the sparsity pattern is different. But essentially, this is a deterministic optimization problem. So if the tree was not too big enough, I could just stick it into Cplex and do it with ample and solve it. All right. Is the model clear to everyone? Yes.
That matrix means, I mean, this one, for example, x2, y is also connected to 3 and 4, from 4 to 3.
X, so let's see here. X.
From 1 you can,
Right, so, okay, so this matrix would not have, so that's right. So this would only have it, you're right, between this block would be 0 in this case. Right, so for,
connected to 2 and 4. And then should be, 3 should be only 3.
there should be empty here. This should be 5 should only be depending on 2. This should be empty here. You're right. Yes. Thank you. Okay. All right. So now let's talk about another formulation. Again, so Jeff alluded to this towards the end of his talk this morning. This is known as a scenario formulation. So what is a scenario? A scenario is, in this case, is a realization of the entire stochastic process. So remember, it is a multi-period problem. Let's say we have 5 periods. So one sample path or one history of the entire realization in all 5 periods. That's called a scenario. Right, so here, for example, a path going from the root of this tree to a leaf node is going to be a scenario. That basically tells us all the data that we have seen in the entire stochastic process. So in this model, we have like 4 scenarios corresponding to the leaf nodes of the tree. And so what is the scenario formulation? So the scenario formulation essentially says that, okay, let me make copies of my actions, my decision variables corresponding to all scenarios. Right? So we have xs of t, the decision in stage t of scenario s. That's what xst is. And yst is analogous. Right? So we have these decisions. So you could solve this scenario problem separately, but obviously that would give me a different solution for, let's say, the first stage. Right? Do you agree with this? If I ignore the fact, so I have, let's say this is a very, there's a lot of rainfall in this scenario, and there's very little rainfall in this scenario. So, but your action now should hedge against both of these options, correct? But if I just solve them independent of each other, then you'd be taking an action which corresponds to scenario 1 greedily, or some other action corresponding to scenario 4. But then they have to be reconciled. It doesn't make sense. So that is done by what are known as non-anticipativity constraints, which Jeff neglected to mention, this beautiful word.
It's my favorite 8-syllable word.
So they're called non-anticipativity constraints, which means that your actions cannot depend on the future. Right? So your actions cannot depend on the future. Your actions should only depend upon the information that you have seen so far. So what are these non-anticipativity constraints saying? So I said xs of t should be equal to s prime of t, where s and s prime are 2 scenarios, which are, this set n, are not distinguishable, indistinguishable up to that time period. I cannot tell them apart at that time period. Right? For example, here, scenario 3 and scenario 4, I don't know which one it is going to be at this time period. Right? In stage 2, I do not know. So I would write x3 of 2, this is x3 of 2, should be equal to x4 of 2, because I cannot differentiate between them. Is that okay? So this is a completely equivalent formulation of the problem. The number of variables have been blown up because I've made copies of them. Is that okay? Here is the third formulation. So this is the kind of what is known as the dynamic programming formulation. So this is, again, you have already seen this in the 2-stage setting when we write a formulation in this way. Right? So what do we do here? We have the extensive form, which involves first stage and second stage variables. we project all of that information into the space of the first stage variables, where everything is captured in this value function, right? This value function basically tells you that, given x, you have to optimize with respect to the second stage variables, and this is the value function of that, right? So that's what the dynamic programming formulation is. So what is the problem? So in the first stage, you'd like to minimize with respect to the first stage decisions, minimize the first stage cost, plus the expected cost of this action in the first stage going forward. Right? Notice here that this expected cost only depends upon your state variables, because I've made this distinction between state and local variables. Just for notational simplicity, I've added ancestor of node 1, but this is basically does not exist, right? So the script Q is known as the expected cost to go function. If you have ever seen dynamic programming, you probably know what these things are. It is the cost from this time period going forward. What is the expected cost of that, right? So what does that depend upon? So the cost to go function in node n, right, depends upon, so this is the cost to go function in, let's say, in this node n, depends upon the state variable at the end at that node, which is a function of that, and that is equal to the expected value, which is, this is the conditional expectation of its children. This calligraphic C is the children nodes of node n. These are the children. There are probabilities. These are the conditional probabilities of going from node n to node m. Right? The previous probabilities that I showed you are the total probabilities. These are the conditional probabilities. So in this case, for example, if all of these were equal probability events, this would be a half. Well, I guess this is not an equal balanced tree, but it would be corresponding that. And Qm is the value function at node m given the state information of its parent. Right? And that is essentially Qm of xn is what? You minimize the cost of that node m with respect to the decisions corresponding to that node, plus the cost to go function going forward from here on. Right? So I just want to kind of, just so you don't get confused with the notation, one thing I just want you to remember, when I write cost to go functions, look, this is Qn of xn. The cost to go function in node n depends on the state, is a function of the state variable at this node. But this value functions, which is Qm of xn, these are the value functions I'm assigning with the children. Right? So there's a little bit of just a kind of notational kind of switch. This is known as the dynamic programming formulation. Is that okay? Yes. No. No, it does, right? So basically, so I have the state variable that I'm carrying through, and then these conditional probabilities are given for, like, at every stage, right? So it's not like this depends on the conditional probabilities for every stage here. So that's already encoded in this probability.
What did you say about the difference between the Qn and Qn?
And P, you mean? P? Oh, so curly Q is the expected cost to go function. This is the expected cost to go function. So if I'm sitting at this node, and so I would like to know what is the expected value going forward, right? And small q is the value function at each of these nodes separately. Okay? All right. Okay, good. All right, so let's go back to this formulation. So here's an exercise, which I'm not going to do, but you can think about doing. So here's the scenario tree that I've given here with the corresponding total probabilities. So one thing that I wanted you to kind of write down was the extensive form of this model. Right? So for every node, so there are 7 nodes in this model. So you introduce 7 sets of decision variables, and you can write down the extensive form with the corresponding probabilities. What is the scenario formulation for these things? So you have to compute the scenarios, the probabilities of each of these scenarios, the dynamic programming formulation, and the two-stage formulation, assuming water levels are decided here and now. If you decide exactly, like H is completely specified at the beginning of your planning. Okay? So consider this kind of as an exercise to think about. All right. So let's talk about kind of the solution approaches for these models. So this extensive form might be too large to solve as one large problem, just because the scenario tree is huge. Okay? So we need to have some decomposition methods, and that has been kind of the theme this morning as well. So I'll talk about some kind of a very simple idea, just to kind of, again, I think that'll answer your question, like this two-stage approximation, and how to use that in some kind of a rolling horizon way to come up with a policy for your actions, for a solution to this model. Then I'll talk about scenario decomposition or progressive hedging, and then I'll talk about stage-wise decomposition and this stochastic dual dynamic programming algorithm, and I'll mention a little bit about nested measures. All right, so let's start with this two-stage approximation. It's fairly intuitive. All right, so there's a lot on this slide, but let's see what is going on here. So there are two sets of models on two sides of the slide. Okay, so here, what are we doing? So this is the actual scenario tree. All right, so it's a big scenario tree, think of it. And so you cannot just put it in your Cplex formulation and solve it, it's too big. So here's one approximation, is that I'm going to say that, okay, let's decide on the values of the state variables up front. I'm going to say, okay, here's how much water I need in the reservoir in every time period. And I tell you, which means that how much water I need in stage 2, the value here is the same in this node and in this node. That's what I'm doing, right? I'm just deciding that there's no flexibility. There's no adaptivity in how much water you can maintain in the reservoir. You cannot adapt that. That has to be fixed. So X is decided, and remember that as soon as X is decided, we have independent problems for every node of the tree, right? But completely, because there's no relationship between this node and that node. The only connection between them is through the values of the state variables. Does everyone see this? Right? This is the actual tree. This is a kind of a approximation or decomposition of this tree. If you tell me what X is, the Y's are separable by the nodes of the tree. Do you all see that? Right? So here's the formulation. So minimize x1 through xt, and this is I already talked about that before. And then basically you minimize for every node. You know, I had a nested formulation. This reduces to kind of a two-stage formulation. The expected value over all the nodes, the actions, yn given x. Right? This is a two-stage model. You've seen this. So this is a two-stage approximation of the problem. I claim that this is a restriction of the original problem. You all see that? Why? Because all I said was that this value of x here and here have to be the same. Value of x2 in this node and this node have to be the same. I just added that constraint in. The value of x4, x5, x6, and x7 all have to be the same. Right? So therefore, it is a restriction. I added a constraint to my model. So it decomposes by node, and then obviously this produces a feasible strategy, feasible policy. Right? Because I assumed that whatever value of x you decide, whatever node happens, there is a y variable or local variables that can adjust, that can fix things up, that can patch things up. Here is another approximation, and this is the one that you were alluding to, is that, okay, let me decide on x1 now, and then going forward, I'm going to forget about these non-anticipativity constraints. Right? So basically, I'm going to say that, okay, I have 4 scenarios. I will have a different x2 for all of these 4 scenarios. I'm allowed to have that. Right? So this is, again, a two-stage model. I'm just deciding x1, and from then afterwards, you can just solve individual scenario problems. So let's look at this formulation for a minute. You minimize the cost of x1, the first stage, plus for each of these scenarios, you look at the second stage cost, and you minimize this. Right? This is no longer a nested formulation, because your x's are kind of, different for different scenarios. You don't have to enforce these red constraints which says that they have to be identical. So therefore, this is a relaxation. I have dropped the non-anticipativity constraints from stage 2 onwards. But this is again a two-stage approximation of the problem. You all believe me, right? This problem, again, it's in the usual setting, it decomposes by scenario subproblems, right? So you have a scenario subproblem, which is multi-period, which involves, let's say, t-1 periods, but it is separable by scenarios. And you can use the two-stage machinery that you have seen this morning to solve these problems, both of these problems. So that gives us a good heuristic to do. You do it in a recursive way. Right? You scan your tree. You start from this node. You solve one of your favorite two-stage approximations. I don't know which one you would like to solve. Solve it. Fix the first stage decision only. Once the first stage decision is fixed, now you have different problems for the different subtrees that are there. And you scan and with different initial conditions, solve the two-stage approximation for the multi-stage problem over subtree Tn with initial conditions specified by the root of that tree. You collect the optimal solution, and you kind of record the x's and y's, and you just repeat this. You basically do it in a recursive way. Right? This is called the rolling horizon framework. Right? You go forward. This is obviously produce a feasible solution, but there's no guarantees. Is that okay? All right. Let's move on. Let's talk about progressive hedging. So now we are going to work with the scenario formulation. Okay. So this is remember again, the scenario formulation is that we have copies of my variables for every scenario separately. This is the scenario constraints. If you know about this method, I don't know if Steve talked about this, alternating direction method of multipliers, ADMM.
He mentioned it, but we didn't get into it.
Coordinate descent methods for convex optimization, right? So you go one coordinate at a time, related type methods. So essentially ADMM, which is kind of a buzzword in convex optimization these days for distributed optimization, is essentially, progressive hedging is essentially ADMM applied to a specific scenario formulation of this problem. So my goal here is to kind of show you that connection if you know about ADMM. Yes?
In your hydroelectric dam example, your demands are your stochastic variables, right?
Demands and the inflows, the water inflows.
Yeah. So assume that they're actually from Rn, right? So your scenarios actually look like just time series.
Yes.
Right? And so suppose you don't construct the scenario tree by discretization or whatever actually. So essentially what you have is a root node, and then scenarios going off and and so there's essentially it's like a two-stage problem, right?
This would be a two-stage problem, but there is what you're talking about is your observations, right?
Yeah.
But there must be some underlying dynamics that goes on. If there is interstage dependencies and so on, if they're completely independent, that's good. Then the interstage dependencies are basically just some kind of Markovian, right? You can go from high rainfall to low rainfall or to another high rainfall. There's no interstage, but there could be interstage dependencies. And how you model that is a very, very delicate and difficult question, which I do not know the answer to.
But condition on what you know right now,
yeah.
The stochastic process that you're sampling from will actually incorporate those dependencies, right? I mean, if it is true that you don't go from a rainy period to a dry period, your scenarios will show that. Except these are now continuous scenarios, so you'll have 0.1 as the rainfall and 0.9 as the rainfall.
But when you say your scenarios will show that, what I'm looking at historical data, or you have?
This is a sample that you generate.
From where? From what?
From a distribution that you know of.
So I know the joint distribution, and I know the actual dependencies, right? So yeah, then there is something like this underlying it, right? Okay, maybe this might be extremely huge, but there is something like that. There is a joint. This is a joint probability distribution, right? Any other questions? Okay. All right. So let's. Now we have these. So I think this is a very, very good question, and it's very, very delicate and multi-stage on how to model kind of these. Like if I give you a set of sample paths, how do you construct a tree where I can maybe Dave can tell us afterwards. I don't know how to do it. How to model so I give you a bunch of sample paths. How do you know where they branch off? Right? How do you create that underlying stochastic process? It's a difficult thing to do. Okay, so let's look at this. So I'm assuming that I'm a kind of a math programming person, so I know that the tree is given to us somehow. It is available to us, and we'd like to optimize this problem. So I'm talking about the algorithms. Okay. So the scenario formulation basically says that. So I have the underlying tree structure. I say that S and S prime have to be identical. another formulation. This is what Jeff had kind of done, introduced this kind of nodal variables, right? This additional variable Zn, which is just the placeholder to equate two scenarios together. So let's pay some attention to the algebra here. So n, now, I'm going to introduce variables corresponding to the original tree as well, right? So for example, here, this variable, xs12 and xs2 should be equal to z2. That's what, this is what these constraints are saying. So I introduce the z variables. So this is what this is. So for all the nodes in stage t, time period t, and all the scenarios that pass through that node, they have to be equal. Okay, this is just a simple reformulation. This helps us to kind of derive the progressive hedging model. So we have 3 sets of variables now. So then what do? So we have these constraints. We write down the Lagrangian relaxation corresponding to this constraint. Right? So you've probably not seen, some of you may not have seen Lagrangian relaxation. So let me just quickly talk about what it is. So essentially, I have the original constraints, then I have these constraints, the constraints in that red box, which I don't like. Right? So one way to deal with them is to add them to the objective with a sufficient penalty parameter. In this case, we're going to my penalties are going to be linear in the violations of the constraints. Right? So some linear functions. Right? So I will add to my objective lambda. Note that these are vectors, right? X and z's are vectors. So lambda times x minus z. I'm avoiding the subscripts. Right? So I have the original problem objective, and I will add these terms. Lambdas are the dual multipliers, or the Lagrange multipliers, which we don't know. But somehow we have to find out to make the problems kind of, work together. Everything needs to work together. But that's essentially, we have those. So we add these constraints to the objective. That gives us the Lagrangian relaxation. Okay, it's a relaxation. Why? Because we have dropped the constraints and added to the objective. If this problem has so if the original problem has a feasible solution, this problem certainly has one. And because x and z are equal to each other, this term goes away. They have the same objective function value. So the Lagrangian problem can only do better. Therefore, it is a relaxation. That's the argument. Okay? So we have a relaxation of the problem. But then we're talking about an augmented Lagrangian. On top of this penalty, note this is the penalty exactly that I added. I also add a nonlinear penalty, a squared difference between these penalties, right? So it was a linear penalty function that I added, but then in the traditional Lagrangian relaxation, in the augmented Lagrangian relaxation, there is a nonlinear term. In this case, it's the Euclidean norm of the difference. All right? So one thing that you have to be careful here is that these Lagrange multipliers have to satisfy dual feasibility. Right? So why is that? Where does this come from? So notice that, what is the best way to write this? So, okay, so again, like I said, there's a lot of notation which I wish to avoid, but maybe I should. So for a minute, ignore this term. Ignore this term, and let's look at this part, right? So the idea of Lagrangian, solving the Lagrangian relaxation is like, because it's a relaxation, it gives you a lower bound. And so you'd like to find out multipliers, lambdas, that maximizes this lower bound. So you you maximize the Lagrangian relaxation, which is a function of lambda, the multipliers, and you maximize it. That turns out to be a concave function, and you're maximizing, so everything is good. But then what happens here is that, notice that, okay, so if you ignore this term and you collect the terms with respect to the x variables, and then you collect the terms with respect to the z variables. And the terms with respect to the z variables, which does not have any constraints here. Notice there are no constraints on z, right? Z is a free variable. The terms that, if you collect the terms with respect to the z variables, this is what you will get. This is exactly what you will get. And that has to be equal to 0, because otherwise, it's unbounded, right? If it was any term, z could be, you could just set z to whatever you want and make the problem unbounded. So then the Lagrangian relaxation would be unbounded, right? So you need to put constraints, and that translates to constraints on the dual variables. That's a constraint that is there. So this just comes from collecting these terms And you can just do the algebra, and that turns out to be that is the constraint that you want to have. Questions? Okay. So now this is just for Lagrangian relaxation. Now let's bring back this term, the augmented Lagrangian term. What is progressive hedging? I told you that is some kind of a coordinate kind of descent method. People call it, like, sometimes if you've seen this Gauss-Seidel type iterations. So you have an optimization problem which involves x, y, z variables, right? So the idea is you hold one set of variables fixed and you optimize with respect to the others. So let's talk about the algorithm. Here it is. Sorry for a lot of notation here. So let's first fix zi, which is my current guess for the node variables, and lambda I, which is my current guess for the dual multipliers. Okay? And you solve for xi and yi. So you need to solve. So zi is fixed. Zi is fixed here. Lambda is fixed. So this problem is separable by scenarios now, right? Because remember, this is sum over the scenarios, right? The only thing, and every variable here is indexed by scenarios except z and lambdas, right? So I fix those. As soon as I fix those, the problem decomposes by scenarios. So each of these problems I can solve separable with respect to each other. Okay? That's the first step. So you solve each of these, for each S, solve these scenario subproblems and collect the corresponding solutions. The next step is to solve for zi. So now I need to solve for zi. If I fix x's, xi, yi, and I need to solve for zi, what is the optimal solution of that one? Zi is an unconstrained minimization problem with a strictly kind of convex objective here. So you can solve it in closed form. Right? So essentially, I mean, look at the term there. So you have, let's look at, so you have, I'll just do it with one. So you have lambda times x minus z plus rho over 2. This is one dimension, right? So I'm just doing a one-dimensional simple exercise. You need to solve this problem. Okay, so maybe it's not, maybe I should put some scenarios here. PS, okay, let's do it. Let's just do this, right? And you need to minimize with respect to z. Remember that these guys are fixed now. Actually, it's I plus 1, but it's I plus 1. Okay? What is the optimal solution of this problem? You can solve it, right? So this is one dimension. You take the derivative, so you'll get, so you get a minus here plus rho times xi plus 1s minus z squared, right? Equals to 0. This is the first order conditions, right? Is that okay? Where is the minus 1 there? This is okay, right? This term is? So remember that, okay, so there is a sum over SPS here as well from this, because this whole thing is in the expected value. This term is 0. Remember, we assume that the dual feasibility says that this is 0. And I'll show you that the Lagrange multipliers are maintained in a way so that that part is 0 always. So if that is 0, what is the optimal? What is z? Z is exactly equal to this rho term. You can just divide from both sides. Is PS times xi plus 1s. Z is the expected value of the solution that you just constructed. Right? So this is you're basically the solution with respect to the z variables can be done analytically, and that's exactly the solution. This was done for a, let's say a two-stage problem. And here, if you do it for every stage, it has to be the conditional expectations corresponding to those things. That's what z is. Is that okay? So you solve for z. So xzi and lambdas were fixed. I collected xi plus 1 and yi plus 1. I computed zi plus 1. And then I need to update my lambdas. Right? And this is done by usual what is called a subgradient step. So here, lambdas are, so you update, you take your previous lambda, and you take a step of rho in the direction of the subgradient of this Lagrangian function. So this is the, remember, if this is a function of lambda, this is the coefficient, the residual. You just need to update. You take that subgradient step. And notice that this always maintains dual feasibility. Why? Because just take the conditional expectations of these things. This is 0, right? By the induction hypothesis, you assume that they're 0. And this is exactly this formula. So therefore, this term cancels out. That's also 0. So you always, your dual updates are in that subspace, or the feasible dual subspace. Okay? Of course, this is the derivation of the algorithm to prove that this actually kind of converges. It takes a bit of work, which I'm not going to do. Right? So under mild assumptions, so let's say you have nice. It works for convex functions as well. I'm talking about linear programs here, but nice convex functions. The sequence of primal and dual solutions converge to an optimal solution of the scenario formulation. This is slightly stronger than the ADMM kind of proof for general problems, because in ADMM, the primal solutions, proving that requires additional assumptions. Okay? But here, both primal and dual, like primal and dual meaning that x, y, z, and lambda, they all converge to the corresponding optimal. Furthermore, here's another nice thing. At every iteration, the values of these nodal variables is a feasible solution. Okay, it's a feasible solution. Why is it feasible? Can someone tell me? How do I know that this is a feasible solution to the original problem? Remember, I dropped constraints, right? But this gives me a feasible solution. Why? Well, that's very easy to see, because each of these x's are feasible to the scenario subproblem, basically, right? And then I'm taking a convex combinations of them, and then I'm projecting onto the where they're supposed to be equal. So therefore, they're all. I'm satisfying I'm projecting onto the additional constraint, where they're supposed to be equal. So therefore, it gives a feasible solution. So you can take those solutions and then evaluate, and that gives you kind of a good solution which you can track how good it is. Okay, let's take a break before we move on to the next part. How many minutes? How many minutes? 2 minutes? 3 minutes?
For any value of rho, or just
Positive values of rho.
But anything
Yeah.
positive?
That's as far as I know, yes.
And they
Rho doesn't need to be changed. You can update rows, but that's not
but you
required.
don't have to.
No.
And is this proven
Yeah.
for any value of rho?
I believe so.
Okay, no, I don't know.
That's what I thought. I mean, I may be mistaken.
Okay, and the proximal term, like what were the assumptions for progressive hedging to
Oh,
converge? You say
LP would work. For example, if everything is LP and bounded, and each of the scenario subproblems are feasible.
So I don't need anything like the xk, the rho x minus xk, so no assumption. Pretty generic.
Yeah, I mean, LP satisfies all of this, all of the required assumptions. In the original problem, is much more general. They do it for much more general convex functions and convex sets.
Okay, but if my original problem is an IP, would anything?
No, it will not converge. In general, I mean, you can easily construct an example where it doesn't.
Like not related to this, but is there anything like if I add a proximal term to an IP, could we say anything about it, or we
Yes, you can. We have a paper where we show that the duality gap is 0 if you choose rho properly and the proximal function properly.
Okay.
That the augmented Lagrangian has a 0 duality. It's in math programming 2015 last year. Okay, so you can start back up. All right, so the final part, I'll talk about. So the scenario progressive hedging used the scenario formulation. That was based on that algorithm was based on the scenario formulation. Now I'll talk about the stochastic dual dynamic programming algorithm, which is based on the dynamic programming formulation of the problem. All right. So just to again remind you what the dynamic programming formulation is. So the overall problem you can think of as this is the actual problem we are interested in solving, right? We are minimizing the first stage costs and with respect to the first stage actions, first stage costs plus the expected cost of whatever is going to happen after that, given as a function of my first stage action. This is the entire problem. That's what we are really interested in solving. Obviously, the problem is I don't know what this function is, and now we open it up like onions, where we are kind of peeling away the layers. So this is Q1 of x1 is the expected cost to go function that requires you the which has a form which is where you take the conditional expectation with respect to the value functions of each of these child nodes, and the problems in each of these child nodes consist of their decision variables and their cost plus the expected cost to go from there on, right? So they are all kind of recursively and is defined in this nested way. So this is a very complicated function to deal with. So this is the dynamic programming formulation. So here's one nice thing about this formulation is that if somehow I gave you these functions, if I told you what Qn for each of these nodes was, right? So I give you the explicit formula for these functions. That means I've given you Q1. So you can just solve it, and you have solved the problem because essentially you have the optimal value and you have the optimal action for stage 1. So now how do you find the decision? What do you do in stage 2? Well, I know what the optimal action for stage 1 is. I know what the data realization is. I know what the function is. So you just optimize the problem corresponding to this node, again, because you know what Q is. So essentially so solving this problem amounts to, is equivalent to giving you kind of these cost to go functions. another way of thinking about this, that these cost to go functions essentially encode, gives you an encoding of the actual solutions. Right? So in some sense, I don't have to give you the solution vectors for every node in this tree. I can just give you the functions. Because once I give you the functions, you can compute the solutions. Okay, that's an encoding. So these cost to go functions or expected cost to go functions are important things of interest. So this is just a kind of straightforward extension of the result that you've seen before, that these cost to go function for the two-state setting, you've seen that this value function is convex function, so polyhedral, piecewise linear polyhedral. So by polyhedral, I mean piecewise linear and convex. So this expected cost to go functions in every node is piecewise linear and polyhedral. So we'll just quickly go through the proof of this because you've seen this already. But so we do this kind of in a backward kind of recursion, backward induction. So suppose we look at stage T. We look at all the nodes in stage T, which is M, and suppose the cost to go functions of that node are polyhedral functions. Okay, so consider a node which is in stage T minus 1. Then for all M, which are children of N, this Qm, this is not the calligraphic Qm, right? So Qm xn is this problem, right? So where you have minimized the variables, the cost of that variables in node M, plus the cost to go function in node M, subject to these constraints, where these constraints only depend upon xn, which was the ancestor node. Remember, this is a function of xn. Move this to the right hand side. This is fixed. This is data. Xn is fixed, right? So we move it to the right hand side. F prime is just the sum of these two functions. Okay, it's a convex piecewise linear function because this is by the induction hypothesis. I assume that this was piecewise linear, right? This was linear already, so the sum of two piecewise linear functions is piecewise linear. This is a piecewise linear function. So you can, this is essentially a linear program because you've seen this modeling trick. If it is a piecewise linear function, you introduce an additional variables and constraint and you can model it. So this is a linear programming problem, right? Where xn appears in the right hand side. So what do? We take its dual. So here I'm not writing down the full dual, I'm writing down what is known as the Lagrangian dual, which is equivalent for linear programming, where essentially, so pi is the dual variables corresponding to these constraints. These constraints here, right? There might be other constraints that are required to model this f prime. Piecewise linear function, I will need to add other. I don't care about them. They're all still included in the original problem. I've just dualized these constraints, right? So I've multiplied pi times the difference between these two guys, and here this is the. So this is the kind of the. This is the Lagrangian relaxation, right? So as we have done before, you look at the violation of this constraint, add it to the objective, and you maximize with respect to the multipliers, pi's. This is the dual problem. So what is happening here? So now I just collect terms. I collect all the terms that involve xm and ym. These are this part. That's what I need to minimize. And then all the terms which are remaining, which are independent of xm and ym, which is this term. This thing is independent of xn. This thing does not, xn does not show up. So you can think of this as a value of an optimization problem, which only depends on pi. Xn is out of here. So this is a number. For every pi, this is a number, right? And this is, and then you have the remaining term. So sorry, I also absorbed this part here. So now you're maximizing with respect to pi this affine function of xn, right? This is an affine function of xn. So, and you're taking a maximum of affine functions of xn. So therefore, we know that this is polyhedral as well. So this is a convex piecewise linear function of xn, where the equality follows from strong duality. This is all equality from linear programs and the induction hypothesis, because remember that this was already polyhedral, so I can apply LP duality. So therefore, this is convex. By LP duality, the number of dual solutions, extreme dual solutions are finite, so therefore this remains polyhedral. And so this is for Qm, and the script Qn is just the expected value of that, and it's a finite expectation, it's a finite sum, so you still have polyhedrality. Okay? So basically, all this saying is that these value functions are polyhedral functions. So there is hope of encoding them in a way, right? So I told you that if I give you the functions, you have solved the problem. So I can give you the description of these functions, for example. And that's what we are kind of getting at. So somebody was asking this question, right? So now we're going to make a strong assumption for this stochastic dual dynamic programming algorithm to work. So we're going to assume that the realizations in every stage are independent across stages. Right? So what we have is a stage-wise independent process. So stage t has nt. So let's assume that n, forget about the subscript t, we're going to have equal number of realizations in every stage except the first one. First one is deterministic. So then we have what we know as a recombinant scenario tree. Right? So essentially, so this is stage 1. In stage 2, one of these 3 things can happen. In stage 3, again, there are 3 possible realizations, but you can come here from either this node or this node. But these realizations are the same, regardless of what had happened, because it's independent. Right? It's like maybe there is like a Markov chain in the background where these are the kind of the states, right? So you have the transition matrix, and you can go from any state to any other state, and the probabilities are assigned to us. Is that okay? So now we have a scenario tree which looks like this. This is not a tree. It's called recombinant tree or some other kind of object here. So what does this do for us? Why is this useful? So the reason it is useful is because now our cost to go functions kind of only depend on the stage we are in. Right? So I need only one function per stage, not per node. The number of nodes here, if you think of this tree, how many nodes does, if I expanded the actual tree, how many nodes would this have? No? 28, right? 28 nodes, right? But so I would need to maintain in this problem. I would need to maintain 10, because the last one does not need a cost to go function. I would need, so if you go back, if you take this guy and expand it out in this form, you get kind of 28 nodes here. The last period, I don't care about the cost to go functions. So if you go back and you want to have a cost to go function for each of these guys, you will need 11 cost to go function that needs to be maintained. Here you need to maintain 7, right? So sorry, you need to maintain 3, 1 for here, 1 for here, 1 for here, and so you can do this exercise and see that this is a big compression from what is these cost to go function that you need to maintain. Does everyone understand why this is the case? Because so let's talk about this here. So the cost to go function at this stage. So let's look at this stage. At this stage is basically the same whether I'm at this node or at this node, because from here I can go anywhere, right? So the cost to go function is the same. It does not depend upon where you are at this point. So it only depends upon at what time period you are in. Of course, the arguments depend upon what history, what you have seen. That your arguments, the functions, where you're evaluating them depend upon what you have observed. So this stage-wise independence is a very, very important property and kind of helps us a lot. As I mentioned before, now, because I have only a small number of cost to go functions that I need to know, and these implicitly encodes my policy, right? My actions. How do I? So a policy is basically a mapping from my information that I've seen to the actions. So if I give you a scenario tree, basically a policy, you can think of it as a table. So if you're in node n, this is what you do. That's how one way to encode a policy, right? So here we have, but we don't need to have this kind of table. It is implicitly encoded in these functions because under jth realization, so if I'm in stage t, and suppose this is the realizations, I know which stage I'm in, which realization I'm in, and what action I've done in the past, then you can easily compute what you need to do now just by solving this problem, right? Because q, you know what q is. You know what xt minus 1 is. You know what j is. So you plug those in and you solve and you find out what your action should be now. So it's an encoding of the actual solutions. Is that okay? Good. All right. So one thing you mentioned is, so how do I construct such a scenario tree, right? So if I knew the underlying process was stage-wise independence, for example, suppose I know that the parameters that I have in my model are independent. Suppose the rainfalls are independent. Let's suppose we are doing yearly things, and so in every year they're independent of each year. Maybe they're not, but suppose. So one way to generate them is like, okay, just generate, because now I know the distribution in every time period. They need not be have the same distribution. They might be different in different years, but they're independent. So you generate the samples. So this would be the samples, essentially. So of rainfalls in year 1, these are the possible realization. These are the rainfalls in year 2, and so on. And because you could go from anywhere to anywhere, so this is a valid tree for that. All right. So what Dave talked about yesterday was to create what is known as the sample average approximating problem for two-stage problems, where basically you generate, by sampling, Monte Carlo sampling, you create a set of scenarios. You can do that here, and there is theory for consistencies and all of the other things for multi-stage, which I'm not going to talk about, where you have, and you generate, in the independent case, you have, once you have sampled, you have an optimization problem defined over a scenario tree which looks like that. Okay? So I've already done the sampling, I've constructed the tree. Now what I'll talk about is, so even once I've constructed this tree, this could be a very large optimization problem. Right? So because the number of realizations, let's say there are 50, but then there are, if you solve it as one large LP, this would still be very, very huge. Right? You would still need all the 28 nodes and the corresponding problems, corresponding variables and constraints. So how do I solve that? So I'm going to talk about a stochastic algorithm where we can solve over scenario trees which look like this but are very large scale. You can obviously, if this is not too large scale, you can just ship this whole model to Cplex and solve it. That's one option. But now we are talking about a stochastic algorithm for solving a deterministic optimization problem. This is very important to differentiate. I've done all the sampling, I have all the data, I have a problem which is over this tree, but I don't know how to solve it. It's too big. So I will do a stochastic algorithm. Is that clear? So here's the algorithm. This is what stochastic dual dynamic programming is. Okay? All right. So my goal is to reconstruct these value functions in every stage. Okay? So here is a problem involving 4 stages. The last stage, the value function is 0. So because there's no information, there's nothing to do afterwards, right? So there's no value function here. There is Q1, there is Q2, and there is Q3. Q1 is a function of x1. This is the cost to go function. What happens? It's a function of what I do in x1, and then so on. So remember, and each of these functions are polyhedral functions. They're piecewise linear and convex. Okay? But I did not know what they look like. This is the red dash function that Jeff had drawn. In my case, these are like light blue functions. Okay. It's a one-dimensional picture. This is the state variable in x1, in stage 1, state variable in stage 2, state variable in x3. What does SDDP do? Remember, it's a stochastic algorithm. So I'm going to build up these functions sequentially. So the first idea is to generate a sample path through the scenario tree. Okay, so here is the sample path. This is where the randomness comes in. You flip a coin and decide whether I'm going to be here, here, or there. You have this, and then flip another coin and say which node, and so on. This is stochastically generated. And then once you have this, now I have a trivial estimates of my cost to go functions, right? So here, in this case, let's say I don't have this. This is 0, or let's say 0 is a lower bound, and I have some useless value here. You can just ignore it. And once you ignore it, because now I have the realizations, I know what J is because I've sampled, right? I know. So in every period, I have a J. So now I can solve these problems, and I get candidate points, right? So this is my action that I'm going to do in stage 1. This is the action that I'm computed in stage 2 corresponding to this realization. This is the action that I'm corresponding to do in this state, in Okay? So these are candidate, what I call trial points. Now why is that important? Because this value function is a function of x3 wherever you are. It doesn't depend upon which node you are at, right? So I have generated these trial points. Here I'm showing a one sample path. You could do it multiple points and get multiple. You can generate more sample paths and get more points. But once I've done that, another thing that I should mention here is, remember I compute in this way. I compute x, I solve x1, I get x1, and then when I solve for x2, I need x1, right? This problem depends on x1, so you have to go forward. This is called a forward pass. So now I have x3. I have the value here. I solve all the subproblems, all of them, not a sampling of them. I have all the subproblems in this stage. This stage, I know x3, I know the realization, I know the problem. I know the problem that needs to be solved. And I can get, because now I have evaluated the function exactly, right? Because the function q3, remember, is the expected value of all the value functions of here, right? So I have evaluated the function, and I can get the duals of those, which depends on x3, and add the cut. The details will be in the next slide, if we have time. So we add this cut. So now I have an approximation of the cost to go function in stage 3. Fold it back one step. Now I have x2. Now I go back to stage 2. Now I solve all the problems in stage 2. But in stage 2, I need to know the cost to go function, right? So remember, in every stage, I need the action from the previous stage, the realization in that node, and the cost to go function of the future. Those are the three things that I need to solve the problem. In this stage, I know the action from the previous stage. That was x1. I know all the realizations, but I do not know the cost to go function, so I'm going to use the approximate one that I just built. So this problem here is an approximate problem, where this guy is replaced by the approximate cost to go function, not the real one. And because of that, notice that this cost to go function, this cut is not tight. I have not evaluated the function exactly because I do not know, the next step is not exact. It's a loser cut, right? So I add this cut. And you go forward and you repeat the process, right? So now you generate another sample path, and you add a cut there, and you keep going, and this goes on until you have built a sufficiently good approximation of these cost to go functions in the first stage. Okay, so let's see how much time we have. So I'm going to skip the details here because this is too much notation that's going on here. I just derived the cuts here, which I will not. Okay, so this is a stochastic algorithm. Okay, the problem is a deterministic one, but it is a stochastic algorithm. Why? Because in the forward pass we are sampling. Okay. Now, what do we have in any iteration of the algorithm? We have a current approximation of the cost to go function. So whatever cost to go function you have, whatever approximation you have, that gives you a policy, because it tells you, okay, here is an approximation, just solve it, that gives you the solution for that stage. So therefore, once I take a sample path, at every sample point I'm evaluating this policy. Okay, and the expected value of that policy is an upper bound on the true problem, because it's a feasible policy. Okay, but I'm only doing it by sampling. So this is where the sample average comes in. This is the forward pass gives you an unbiased estimator of an upper bound on the true optimal value. I wanted to kind of write that down, but we'll just skip it because we're running out of time. Forward pass generates candidate solutions along sample paths. Average of these objective values provides a statistical upper bound. So it is a statistical upper bound. So there is, you can get confidence intervals by looking at the variances and so on. So the upper bound, so this is the iteration, these are the bounds. The upper bound is stochastic. The lower bound, where do we get the lower bound from? Remember, the real problem is the first stage problem, where I have the actual objective function value, actual cost to go function. That's the real problem that I would like to solve. So the problem in stage 1, if I knew the actual value function, that the optimal value of that is going to be the optimal value. But now I only have A, because everywhere I'm under approximating, I only get a lower bound. So in every iteration, I get a lower bound on the true optimal value, but that is a deterministic lower bound. There is no sampling going on. Why? Because at every stage when I do the backward pass, I solve all the problems. I do not do a sampling of the problems. I solve all of them. So that gives me a lower bound. So the lower bounds kind of, is deterministically increasing. The upper bounds kind of oscillates. And so you have to decide, because it's with some statistical tolerances, when you want to stop, and so on. Okay. I don't think we'll be doing any proofs. I wanted to do a kind of a proof of convergence of this, but I will just give you some history, which I learned in the stochastic programming conference, this meeting. So this is the original paper that proposed this algorithm. It's a very, very highly cited paper. There's been a lot of follow-up work. Mario Pereira is, do I have a picture? That's him. That's Mario Pereira. So this algorithm is actually used in Brazil for kind of a lot of their hydro scheduling and operations. So this is kind of whenever somebody asks, have you seen a real-world application of stochastic programming? Multi-stage stochastic programming, here's a serious one. So this is called the Brazilian, that's why some people call it the Brazilian algorithm. Here is the number of papers that cited this SDDP paper, and recently kind of it is spiking because there's been a lot of work in kind of energy. The other kind of interesting anecdote apparently is this paper was written, or this idea was while this guy was in jail. Apparently, right? That's what he said. He was picked up by the police at Rio airport for whatever reason, and so he was incarcerated during the time this paper was, when he worked out this algorithm. Okay, so convergence result. I'll just mention it without proof. The kind of some ideas of the proof are in the slides, and I can talk about it if you want later on. So if the sampling is done with replacement, so because these are independent, but we do it by replacement. And when we are constructing these cuts, we do it the same way as we do it in the two-stage model. You have to solve the dual problem. You get extreme points. And if you use basic dual solutions, essentially extreme points of the dual feasible region are used to construct the cuts. Then with probability 1, this algorithm converges in a finite number of iterations to an optimal policy. So policy, remember, is defined as soon as you have the value function approximation for this problem. Okay, so so finite number of iterations with probability 1. So that's there's a little bit of subtlety there, but essentially what this means that there is, with probability. Well, we'll have to write down the thing formally, which I didn't write down here, to see what this means. So essentially, the probability that the algorithm does not converge in a finite number of iterations is 0. Okay. Okay. I'm not going to do the proof. Okay. So I think we should finish. Let's see if I wanted to add something else. Okay. Let me just quickly finish by this nested Bender's algorithm. So this is a precursor to the SDDP method. This was before SDDP. So here, now this algorithm is for solving, it's a deterministic algorithm. It's not a stochastic algorithm. There's no sampling involved when the tree is given to us. So in other words, we do a forward pass. In the forward pass, we have x1. Then we solve all the subproblems corresponding to the next stage, all the nodes corresponding to the next stage, right? Then we go forward and we solve all the subproblems in the nodes corresponding to the stage after that. In this case, we are trying to construct these value function approximations for every node, not for every stage. So it is a deterministic algorithm. So implementations of this algorithm are actually have been done by several people, and so Gus Gassman, Donahue and Burge, and Alan King. In fact, there was a software from IBM that did it, IBM OSL SE. Right. All right, so some selected references I think I'm going to finish. Thank you.
So when you solve this multi-stage problem, right, you essentially have for every scenario, you actually have the x and y variables determined, right? So once you solve it, there is no need to solve it until you reach the end of time, right? End of your horizon.
Right.
So don't you actually gain anything from having the ability to update your x's or y's?
If your information has changed, right? Just
No,
that's
the,
what.
no, the scenarios are revealed to you, but the distributions have not changed.
So nothing has changed. So have you, when you constructed this multi-stage problem, is it an approximation of the real problem, the true problem, or is this?
Assume that it is actually the probability distribution as well is known to us.
So but it is like, you know, and it is given by the tree that I used.
Yeah.
Then you don't need to solve it.
You solve it once until that.
I've gotten all the information, right? But that's why. But obviously, it's never the case, right? You always have. You've probably used an approximation of some kind. Some information has been revealed to you. That's why I talked about, let's say, this two-stage approximation, where you do it. That allows you to adapt to the information also. Maybe you have a better estimate of your underlying stochastic process.
And do people do multi-stage optimization, but update it at every step? They do that.
So, yeah. So, you know, I mean, in fact, that you do implicitly, right? So you plan for, let's say, this hydro planning problem. Just plan for 5 years. They are not going to, like, you know, hold them to that schedule for 5 years. They'll obviously kind of replan every once in a while. Right?
Now, in your example, you have the recombinant tree with essentially independence between the stages. But a more realistic scenario is actually a recombinant tree with paths having different probabilities. Can you apply something like the SDDP to a situation like that?
Paths having different problems.
So you have essentially a directed acyclic graph like you have, but all the paths don't have the same probability.
All the paths. So.
Oh, I'm sorry.
You mean the transitions?
More than that. I'm saying that they're not independent of each other.
They're not independent of each other.
Yeah.
So then you would get a real.
Stages are not independent of each
Yeah.
other.
So then you will get a full scenario tree.
Right.
So you still can do that, where basically, but then you need to. You don't get this compression that I talked about. This. I don't have this property, right? No. Where is this? Okay, right. I don't have this. Come on. I don't have this property, right? I have to have a value function approximation for every node. But you could build it up by sampling. You could do a nested version of you could do a stochastic nested algorithm where you don't scan the entire tree going forward. You only sample.
And on the situations where the Q functions, the calculated Q functions are dependent on the node, but not on the stage. So
nodes, I mean, node has to specify the stages, right? So whenever you talk about node, there is an associated stage with it.
I know, but so you assume that you can label an ABC for each stage, yes, right? So are there situations where the Q functions are different for each of the nodes, so A, QA, QB, and QC, but they're not dependent on the time?
Oh, sure, yeah, that can happen. There is some kind of, for example, if there was a Markov, there's a Markovian process underlying whether you have, so that could happen. Yes.
Is that never explained that in SDDP?
I think Philpott, right?
There's a couple things you can do, right? So one is if you have an autoregressive dependency policy, then you can do SDDP.
Sure.
And one way to think about it is, you don't have to do it this way, but a clean way to think about it is you just introduce an extra decision variable that tells you what the inflow or the demand was in the previous time period. So you increase the dimension of the state, and now you have independence in this higher dimensional problem.
Yeah.
There's smarter ways to do it. The other thing is the Markovian bit.
Yeah.
So you can have like 3 parallel trees like this, where you're in a financial problem where markets are volatile or they're normal, right? And then you can do SDDP in each of those planes.
Yes.
So yeah, there's ways to capture dependency that's sort of in between
Yes.
these
Completely,
two
yes.
extremes.
Thank you. Yes.
So can you talk a little bit about the size of the problem and this method apply?
Size of the problems. Okay, good. So the most important dimension is dimension of the state variables. Right? So here, because we are going to build approximations of functions which are functions of state variables here. So that dimension is important. So for example, in this hydro planning problem, the state variable is usually small, like just maybe the number of reservoirs you have, because that's all you need to maintain. So if that blows up, this algorithm is going to suffer. The other important is, like, of course, the number of stages is important, right? Because the more longer stages you have, the problem can get, this method is going to suffer because the approximations, you have to kind of go back and forth. And of course, the number of samples that you have, the size of the tree essentially is, of course, very, very important. So to give you like concrete numbers, it depends on the applications. So people have solved like 40, 50 period problems with 50 realizations per stage, and maybe 10, 12 dimensional state variables. Again, it's important to note the state variables. That's why I separate the state variables. This could be quite large. Y's could be much larger. Dave might have more information.
In Brazil, they'll either have 4 aggregate reservoirs,
Yeah.
or they'll have on the order of 20
Yeah.
finer reservoirs, and they'll solve a 10-year problem with monthly stages, so 120 total stages, where the number of branches at each stage is 30-ish,
Yeah.
30, 50.
Yeah.
And they'll do those, they have autoregressive models with lags of up to 6 months for the inflows.
So the X in that case is
The X is either 4 or 20.
20, yeah.
but the Y is kind of like not.
Y can be a
Y
lot
can be
bigger
a lot.
because Y is incorporating thermal generators.
Transmissions and all kinds of things, yeah.
So if you wrote the extensive form, you have to show off. If you wrote the extensive form, it would have like
So-
2.7
Trillion.
trillion.
Yeah.
you
So
know,
we have
you know.
stochastic integer programs, so you have trillions of variables in the extended form, which doesn't make.
Yeah, so maybe 50 to
Yeah.
the power 190.
Yeah, yeah. That's if you had one state variable. Yeah. So,
This is only applied to the linear function. Right?
this is only applied to linear problems, as I've described it. Yes. There has been work on applying this to where you have kind of some nonlinearities, and sometimes for certain classes of stochastic integer problems as well.
But as I know, that hydropower is kind of like a nonlinear function.
Yes.
But maybe they use some linear function.
They approximate the kind of conversions linearly, typically. There is work on that as well, right? So to like look at the explicit functions and exploit the type of non-convexities you have there. There's been recent work on extending this method to that as well. Any more questions? Okay, thank you.